Okay, should be live. Requires some kind of external validation. Global. Yeah. There you go. Anton says 4K. All right, so the 4K works. So we've got a new design for the layout. We've got 4K as the output stream, which appears to be working. We've done a little bit of color correcting. I've boosted the gain on my mic a little bit. Any more? I'll go up to 12. At a certain point, it just is going to turn into noise. But yeah, people always say that I'm 20 frames a second. Okay, let's see if we can. Audio bitrate, video. It says 60 frames a second. So do you want me to go back down to the 1080, Anton? Okay. Okay. Yeah, we've got some color correction. We've got a little bit of gain on the audio. Let me know if it's getting too loud. I think I have still a little more room. Let me boost the gain a little bit more. Go up to 14. People always say that I'm a little too quiet. So this should make it, I'm pushing into the yellow right now, every now and then up into the red, but I think that'll be fine. So, okay, cool. And then we've got a new design here on the layout. So cool spacey background. That's all the hard work of producer Anton. Not that Anton. Oh, FPS good, just a joke. Yeah, go ahead and joke with me, Anton. Yeah, it's a good time for that. People are asking if it's legal to talk about 420. I'm Canadian, and so marijuana is legal in Canada. So therefore, yes. Okay, let's get on to the first question. Paul Oryx. Chemical rockets and parachutes. When are we going to get beyond that? It's like SC's rockets is our space program. Yeah, it is funny that the chemical rockets and parachute systems that were developed at the dawn of the space age, when you look back and go to see the first flights of the Soviet rocket program, of the original Mercury capsule and the Geminis and the Apollos, they look very similar to the kinds of rockets that they fly today. And the problem is that the technology to make something vastly different just kind of doesn't exist. Well, it's not entirely true, but chemical rockets get the job done. They have a very high speed of exhaust gases out the back of the rocket, which imparts a lot of velocity to the rocket itself. There are other propulsion systems that have been tested, even some that have been used in space. The main one of these is the ion engine, which is incredibly fuel efficient, using a magnetic field to accelerate ions at the back of your spacecraft. You use solar power to power. You use energy from the sun to provide the electricity, which then can send these ions out the back of the spacecraft. This is what's used also for all of the Starlink satellites. And there have been other ideas for more advanced forms of rocketry. When you think about, say, nuclear rockets, where you run a fission reactor and you're using the heat coming off the fission reactor to heat up some exhaust gas like hydrogen, you blow that out the back, you can get a much higher velocity out of that kind of a gas than you can with what a traditional chemical rocket is. And there's a few other improvements that you could make, but running a fission reactor as your way of getting your spacecraft off the surface of the Earth, there are people who might have environmental concerns about that. And so we'll probably see nuclear rockets used in space. And then you put those ideas together. You have a fission reactor that is together with an ion engine. So the fission reactor is producing an enormous amount of electricity that's being used to accelerate the ions out the back of the rocket. This is a Hall effect thruster. So they're very powerful ion engines. Now, nothing as powerful as a chemical rocket. Like, while an ion engine might give the kind of thrust like you could feel like you're holding a piece of paper, the force of gravity of a piece of paper on your hand, that's the strength of an ion engine. And with this more powerful one that I'm talking about, maybe it's a few pieces of paper on your hand, but it translates to a larger, a bigger change, a delta V for the spacecraft. But the reality is that just nothing gets the job done like a chemical rocket. Now, when you're coming back to Earth, the atmosphere of planet Earth decelerates your spacecraft. And that's why you use a parachute, that trying to use, some kind of propulsion system to actually slow you down so that you could then land propulsively is incredibly expensive. Now, obviously SpaceX uses that for the landing of their boosters, but they're only going a few thousand kilometers per hour. They are not going orbital velocity. And so it's really hard to turn your back on the free lunch that the Earth's atmosphere gives you to decelerate your spacecraft. You use an aeroshell to make your way through the atmosphere of the Earth, then you deploy parachutes to slow yourself down so that you can just land gently in the ocean. I think even if we had antimatter rockets that were carrying spacecraft off the surface of the Earth, fusion drives that were taking us into space, people would still want to use parachutes to slow themselves down because it is just a free lunch. But yeah, it would be great if there was better technology, and maybe we should see maybe we should have the world's countries invest more into space exploration and less into other activities. But man can dream. You don't need to put the big question mark in the chat, Hensel. You just your regular question mark does the trick. So, hey everybody, welcome to the weekly question show, the live stream. So go ahead and put any questions that you might have into the YouTube comments, and then I will grab a bunch of those questions and answer them here. We've got a couple of moderators. I see Anton is here and Zapvan is here. Others might show up. So now just some ground rules. I try to give emphasis to the people who've never had your questions answered before. So if you're looking for a reason, you're on the fence, you don't know whether you should ask your question, go ahead. It's a safe space. The second thing is, remember that I am a journalist, not a scientist. And so I cannot provide you original opinions about the cosmos. I can merely report on the scientific consensus that other people believe. And then, of course, we get a lot of questions during these shows, and I try to mix them up and make them as different from each other as I can. Although obviously we come back around and answer the same questions on a regular basis, but still, so don't ask your questions a bunch of times. We got it the one time. It's there, and it's in the database, and I can see it. So don't worry, it's safe. But I might not answer because I don't know the answer, or because you've asked a question that requires too much math, or that it's a question that we've gotten a lot of, or I've just run out of time. I try to get through as many of the questions as I can. But I still get through about a third of them. So, but I will do what I can. All right. Okay. Let's get into the questions. What do we got? Liam Dobbin. If we were to get 10,000 digital telescopes synchronized and focused on a particular star system, such as TRAPPIST, would they be able to collect enough photons to image planets? So there are two ways that you can add together the light of a bunch of telescopes. The one way is that you are adding them where you are collecting photons individually on all of the different telescopes, and then you are essentially using all of these data to reduce the noise and produce a better image. And if you took 10,000 digital telescopes and you imaged them at some target, let's say the Orion Nebula, and had them all gathering data at the same time at roughly the same conditions. So let's say you had them arrayed in a desert somewhere, 10,000 telescopes all looking at the same target together. Then you could stack up the images from all of those separate telescopes, and you would be able to produce a better image. That you would have more data, less noise, it would make for a better image. But it wouldn't be enough for you to be able to say resolve something like the TRAPPIST-1 system, because what you need for that is resolution. Actually, for TRAPPIST-1, you also need to be able to block the light of the star, but you need the resolution. And so the other idea is that you build, well, so in other words, if you had 10,000 telescopes, it would be the equivalent of you having a telescope that is as big as the shared surface area of all of those telescopes. So if each one is, I don't know, let's say it's 10 square centimeters, then you would have 10,000 times 10 square centimeters as a sort of resolving area for your telescope. It would be a very big telescope, but it would be sort of roughly on the order of some of the bigger observatories on Earth. So that is the one way that you can do this. The second way that you can do this is you can build an interferometer, and this is where you separate the telescopes some distance, and then you tune the telescopes so that they're observing exactly the same wavefront, down to the photon. So you know, when you think about these photons, they can be 500 nanometers long. You've got to make sure that your telescopes are within 500 nanometers of each other when they're observing the light from the TRAPPIST-1 system. And it is incredibly difficult. But if you can do it, then you get a telescope with the resolution, the ability to pick out small objects that is the size of the separation between the telescopes. So it's less about the size of the telescopes and more about how far apart can you put these telescopes. If you put these telescopes on either side of the Earth, even two telescopes on either side of the Earth, you're going to make a telescope as big as the Earth, which sounds great, right? A telescope that is thousands of kilometers across. That would be a very big telescope. Now, it would only be able to see bright objects, only as bright as what that single tiny little telescope can see. And you had that challenge of making sure that they were dialed into a few hundred nanometers of each other. That's the challenge, that if you walk, if a truck rolls nearby one of these telescopes, then it will no longer be within the nanometers of each other, and then it's off of the interferometer. But the other big challenge is the Earth's atmosphere. The Earth's atmosphere is this soup of sort of fluid air that is above the telescope, that is constantly changing and shifting, and puts a hard limit on how much you can see with any telescope. And so really, before the modern age of adaptive optics, which I'll go into in a second, there was really a limiter to the size, the biggest possible telescope. You could have a telescope that was, say, a meter across. You could have a telescope that was 5 meters across, and the images that you would get from the 5-meter telescope were not going to be a lot better than the images that you're going to get from the 1-meter telescope. It would be faster. You know, you would have much more light collecting ability, but it wasn't going to give you that really nice resolution. It wasn't until the development of adaptive optics where you put this artificial star in the sky, you calculate the turbulence in the atmosphere, you reverse that in your telescope, and you essentially make it as if your telescope is out in space. That was the big technology that unlocked the new mega observatories that we have around the world, the 8-meter telescopes, the 10-meter telescopes, the upcoming 39-meter telescope. They have to have that adaptive optic system to be able to see. So back to your original question, if you had 10,000 digital telescopes, each of which had a tiny little adaptive optic system so that it was able to remove the effect of the Earth's atmosphere. So each one of these little telescopes was firing a laser into space, and then it was using that laser as an artificial star to be able to recalculate what the sky is supposed to look like. And you were able to arrange those telescopes to within a few hundred nanometers of each other, you know, comparatively. So they were seeing light from the same star within a couple of hundred nanometers of each other. Then, yes, but all of those are engineering difficulties, the likes of which you don't even want to get into. So the short answer is no, that generally people build a big telescope. If you're going to build an interferometer, then, you know, there are a couple of visible light interferometers, some infrared interferometers. They're very difficult to build, require incredible engineering. And I've done a whole interview about what it took to build this telescope called the Chara Array, which is an optical interferometer in the United States. And it is like the level of engineering is just off the charts. So you go with the brute force, 10,000 telescopes, all taking images of the same object at the same time. It gives you more data. You can get a nicer picture more quickly. Space Geek Sherry, if Voyager crashes into something or is intercepted, will we know? Or will it suddenly go offline and be a mystery as to what happened to it? Yeah, it would be the latter. That if for some reason the Voyager crashed into an asteroid, then it would be expected to send a signal back home at a certain time, and it just wouldn't send that signal. And you wouldn't know whether you had lost the Voyager because it had crashed into something or whether its hardware had just broken down and it was no longer operational. And that happens all the time, where they're a spacecraft, they're working fine, and then they're expected, the ground control sends a communication to the spacecraft does not respond. And then they try different tricks and techniques to try and bring that spacecraft back into communications. They'll try sending reboot codes. So even if the spacecraft is actually receiving the signals, but just can't return the messages, then it'll receive that, it'll reboot, and then it'll, it's like turning it off, turning it back on again, right? So these kinds of methodologies to try and bring back your spacecraft. And then if that doesn't work, after several weeks of trying, then the controllers will write off the mission, say, well, it lost contact and we are no longer able to communicate with it, and we can assume that it is lost. But we have no information. I mean, if Voyager crashed into a Kuiper Belt object 100 astronomical units away from us, we have no telescope that would allow us to be able to see that happen. It would just be, it didn't check in, it didn't reply, and it's gone. And whether it was an alien spacecraft picked it up, or whether it crashed into a Kuiper Belt object, or it just broke, we would never hear from it again. Han Solo, do you think we found marks of past primitive life on Mars? Well, we have no certain... There have been some really interesting discoveries on Mars that have said that maybe one explanation is that this was caused by life, but there are other viable explanations. And there's sort of three main... There are three main discoveries in the last couple of decades that have led people to believe that there may have been life on Mars, or there might still be life on Mars. The first one was the Viking experiment. And in this, Viking was a mission sent in the late 1970s to Mars, and it was able to scoop up some regolith and then put water and some nutrients in with the regolith, and then it was detecting if any kind of gas was coming out of the regolith that would be indicative of microbial life living in that regolith. And that it did detect some kind of output of gas, but there have been arguments to this day about what it was that it found. One camp believes that it is evidence of some kind of bacterial life in the regolith on Mars. Another camp believes that this is just some kind of abiotic process, that it's just chemistry, that something reacted. Maybe the perchlorates with the water produced the gases, and you got this result. And so right now, if you go and talk to people, some will say that they found life, others will swear that it didn't find life. The other big discovery that happened was that around the Curiosity rover on Mars, they detected an increase of methane in the environment during springtime on Mars. And this led some people to believe that this is some kind of, the temperature was warming up, and this was causing methanogen bacteria on the surface of Mars to kick into high gear and start to output methane around the environment of Curiosity. But others think, well, maybe it was caused by the rover itself, that maybe it was settling or was rolling over the ground, and it was interacting with its environment to release methane into its environment. But other spacecraft have detected what seem to be increases in methane in the area around Curiosity, around Mars. And so one possibility is that there is some kind of bacteria on Mars that has produced this methane into the atmosphere of Mars. But there are other, again, non-biological ways that you could get this, that there could be volcanoes on Mars that are producing methane. And maybe as Curiosity is rolling across the surface of Mars, it is compressing gas in the regolith, and is sort of causing it to be expelled around Curiosity. But the one that's more interesting, very recent, was a discovery by, was it Perseverance or was it Curiosity? It was the sulfur-bearing minerals. Make sure I got the right rover. It was so it was Curiosity. Yeah, okay. And there was that rock, that Curiosity. Let me get the name of the rock. That was from Perseverance. Okay, all right. And then the other example, most recent, is a discovery by the Perseverance rover on Mars. And it found this rock that had these stripes in it and these weird little spots in it of iron-bearing compounds. And that these kinds of rocks are produced by life on Earth. And so this could be an example of some ancient life form on Mars, back when Mars was a lot more habitable early on in its history, that was producing these iron compounds, and they were being sort of fossilized into the rock. And Perseverance has taken samples of this rock, and now, you know, they need to be brought back to Earth by the Mars Sample Return mission to be able to find out. But the scientists that were involved with this said that they'd essentially exhausted every non-biological source that you could get this kind of formation. And so all that remains, in their opinion, was some kind of biology that was actually creating it. But, you know, that doesn't mean for sure that it was life. There could be some non-biological process that they weren't familiar with that could create this. So this is possibly the most important discovery that humanity could make scientifically. Like, if we find life on Mars, then that means that life is probably everywhere across the cosmos. And so you got to be sure. And so even if there was a tree on Mars, even if there were aliens waving to us in the cameras on Mars, we would go, I don't know, what are the non-biological ways that you could get this happening on Mars? And people would probably be very, very reticent to fully jump in right away. But if the evidence is overwhelming, eventually, right? Eventually we will have a spacecraft go to this location, pick up the samples from Perseverance, bring them back home to Earth, and then scientists will be able to study these in the lab to find out whether or not it was truly life. So this is a long, complex detective work to be able to get an answer to this question. David Evans, would it be possible to use the radiation of space to power spacecraft? So it is theoretically possible. The kind of, there's two kinds of radiation that you can get out in space. Actually, there's many kinds of radiation, but the ones that you're probably thinking about are the trapped radiation, the ones that are around, say, Jupiter. The other kind is, say, cosmic rays. These are high energy particles that have been sent from pulsars, from supernova, from supermassive black holes. They're the ones that give you that destroy your DNA as they blast through your body, potentially giving you cancer down the road. It's this constant stream of these cosmic rays that are going through your body. So could you use those to power your spacecraft? Theoretically, if you had some way to be able to catch these high energy particles and then extract the energy from their velocity, then yes. But the challenge is that is a very complicated thing to do. You essentially need to create a very powerful magnetic field to direct the particles as they are coming towards you. And then you would need to somehow decelerate the particles and then use that deceleration to provide electricity for your spacecraft. It sounds very complicated when you could just use the light that is coming from the star, which is a kind of radiation, and you are able to power your spacecraft. So although we could probably come up with some kind of engineering solution to extract some energy with a powerful magnetic field coming out of these cosmic rays, it would probably be a lot more trouble than it's worth, as opposed to just opening up your solar panels. And then the other way is the trapped radiation, the particles that are buzzing around the Earth and buzzing around Jupiter. And same thing, like theoretically, that those particles, as they pass by, they're going to induce a current in a magnetic field, right? You're going to get, if you have a magnetic field, you should be able to get some kind of electricity as these things are going by, but it's not enough. It's not happening quickly enough that you could really kind of count on it. Instead, you just use solar power. Incomore. Now that Galifianakis is living on the remote BC island of Denman, and that's only that far away, do you guys hang out together and do famous people things? So, oh man. Okay, Zach Galifianakis, if you're watching this, you need to shut this off, because what I'm about to say is going to make you very sad. Okay, you ready? You chose the wrong island. So I live on Vancouver Island, which is the giant island on this west coast of British Columbia. And then Denman Island is the island that Zach has gone to move to. And it is this small island just south of the city that I live in. And then I grew up on the next island over, which is called Hornby Island. And it is a little bit smaller than Denman Island and way better. It's this awesome island with beautiful sandy beaches, incredible mountain bike riding. It is just a really great island. Denman Island is cool. It's got a bunch of forests on it, but it was mostly just the island that we drove across every day going to school, because I would catch the bus on my island. We would catch a ferry over to Denman Island, drive across Denman Island on a school bus, then get another ferry over to Vancouver Island, and then I would catch the bus into my high school here on Vancouver Island, in the city that I live in now. So I grew up on Hornby Island. My father still lives on Hornby Island. I've sort of entertained, like, would I want to live on Hornby Island? And a bunch of my friends have actually moved back to the island, and I couldn't bring myself to live back on Hornby Island. It's just too isolated. Where I live on Vancouver Island, I'm in the middle of nowhere. I live on this island, and yet I can go to a Costco, movie theater, go to restaurants. You just can't do that on Hornby Island. Denman Island has a late ferry, but yeah, he picked the wrong island. He should not have moved to Denman Island. He should have moved to Hornby Island or Vancouver Island. So if Zach is watching this, there's still time to back out of your contract, and I can suggest some better places to go than Denman Island. But I hope you enjoy it there. And let me know when you want to hang out and do famous people stuff, like gardening, because I am a excited gardener. Klondike 69 None. Is there an escape velocity to leave the Milky Way just as there is to leave the Earth's orbit? Absolutely. To leave the solar system, you need to be going about 50 kilometers per second to leave the sun. But the Earth's orbit, it's 42 kilometers per second. Yeah, to leave the sun. The Earth is going 30 kilometers per second around the sun. And so you can subtract that 30 and you're left with about 12 kilometers per second to escape the solar system and go out into the Milky Way in general. The escape velocity for the Milky Way is above 500 kilometers per second. And so if you can get a star that's going above 550 kilometers per second, then you'll be able to escape the Milky Way. And this is a thing that happens, that astronomers have used Gaia to look across the Milky Way and have detected stars that are on their way out of the Milky Way because of some kind of interaction here within the Milky Way. One possibility is that if you get too close to the supermassive black hole at the heart of the Milky Way and have some interaction with some other star when you're there, then you can be kicked out on this three-body interaction to leave the Milky Way. Another possibility is that if there's like a star that is in orbit around another star and then the star goes supernova, then the remaining star is catapulted out of the Milky Way. And we see examples of these stars that are on escape trajectories, hundreds of them leaving the Milky Way, some faster than 1,000 kilometers per second, which is, what is that, like 0.1% the speed of light? Like very fast. So, yep, absolutely. And then there are escape velocities to leave the local group and escape velocities to leave giant galaxy clusters out there. There's always an escape velocity until you reach the escape velocity of a black hole, where then you need to be going faster than the speed of light to be able to leave the thing, and you can't. Giohondo, is it possible that we may find an actual skeletal fossil on Mars, or would it be all gone by now? If there are skeletal fossils on Mars, and they're not that old, you know, maybe they are hundreds of millions of years old, then theoretically we could find them. It all depends on the preservation, depends on the conditions of Mars. Like, keep in mind that Mars has been incredibly dry, cold, has not had a lot of active erosion on the surface of the planet beyond wind. And on Earth, I mean, we've got water, we've got temperature changes, atmosphere, we've got biological erosion that is going on. There's a lot going on to destroy various landscapes and reveal the, you know, and destroy any archaeological evidence of past life. But on Mars, it is cold and dead. And so but it also doesn't have the same kind of like plate tectonics that can reveal older features. But, you know, here on Earth, they have found examples of bacterial colonies going back to 4 billion years ago. And so theoretically, the same kind of thing could be found on Mars. They're called stromatolites, I think. So they're these bacterial colonies that form these sort of rock formations. And so this is the hope that we will find these kinds of structures on Mars, and then that would be evidence of a past, some kind of past life form on Mars. But what you're talking about, like, what if there was like a dinosaur fossil, right? Like, that would be very cool. And it would just depend on the conditions of what it was preserved in, and then how much erosion has happened to get to the point where it's at right now. Yeah, it depends on the age. You know, how long ago would there have been animals on Mars? 500 million years ago? So it would be the same thing as Earth. Dad a monk. With moon colonization imminent, will the international community establish a universal time for the moon? How will that work, and will time dilation have to be taken into account due to low gravity? So the international community is working on plans for a moon time zone right now. And you're exactly right. Like, the problem is that the moon is not locked to any one specific spot on Earth. The moon goes around the Earth. And so it spends time in all of the different time zones around the Earth and then returns back over the course of its lunar month. And so what time is it on the moon? Well, you can't use what time zone the moon is in to tell you what time it is. You have to come up with this separate time zone. And then you're exactly right about the relativistic, the time dilation problem, which is that clocks run slower in larger gravity wells. And so the Earth has a larger gravity well than the moon does. And that means that the clocks will run slower on the Earth than they do on the moon. The clocks run faster on the moon. And so any highly accurate atomic clock that is put on the surface of the moon will lose time compared to its twin clock that is on Earth, which is such a mind-bending idea that the moon is like, it's literally just the difference of the gravity wells. If you had the two atomic clocks lined up and you were just watching them, you could watch the time drift on the two clocks because of the difference in the gravity wells. It's crazy, but it is true. So they are planning to account for all of this. So there will be a lunar time zone. It will account for the time dilation that you experience on the moon compared to what you experience on the Earth, and give a way of being able to communicate. And you need it to be very, very accurate. I mean, you're talking about communicating with the moon and making sure that you've got the time codes correctly. You're dealing with orbital maneuvers that have to be done at very specific times. It is imperative that they come up with something and that it is shared around the world. So hopefully by the time we do have moon colonies, we will have a well thought through time system. Whoa, did something happen to Juno? No, everything's fine with Juno. Oh, wait. Okay, hold on. I don't see any problem with Juno. There's a problem like a year ago. Okay. So sorry. Mag's Place is asking, do you know what happened to the Juno spacecraft? Is it still alive? Juno is the mission, the NASA mission that is orbiting Jupiter. And from what I understand, it's still operational. I haven't heard any news of it going offline. But if someone has something different, please let me know. Greenwich Moon Time. I don't know what Cloud 9 is. Someone's asking a question about Cloud 9. Is that a black hole? Transition limited H1 cloud, starless dark matter. Okay, all right. I know what that is. Okay. Christian DeSalle. Fraser, since there are no stars in Cloud 9, does that also mean there are no planets? So Cloud 9 is a cloud of hydrogen that was detected by China's 500-meter radio telescope, the FAST Observatory. And it has millions of times the mass of the sun, but doesn't seem to have any stars in it. Probably has dark matter associated with the hydrogen gas. But it probably does have some stars in it. It's not like there's no stars. But even if it does have stars, if it's not in this place where the stars are enriching each other with their outflows of heavier elements, supernova, colliding neutron stars, the winds of dying red giant stars, then you're not going to get the kinds of heavier elements that are going to be able to form up planets. So even if there are the occasional star in that gas cloud, that you probably wouldn't have very interesting planets. Maybe hydrogen, maybe planets that are made of hydrogen and helium with a little bit of enriched heavier elements, but not much. Juan Mendez, what is the additional value of gravitational wave observatories other than studying black hole or neutron star mergers? We are still in the very nascent stages of gravitational wave astronomy. And so the first gravitational wave observatories that were set up, the LIGO instruments, were designed to detect the most detectable gravitational wave events, the mergers of black holes that are in the sort of 10 to 100 solar mass range, that gives off a very specific kind of gravitational wave signature that is detectable by our instruments. But there are so many other kinds of events that produce gravitational waves that are just beyond the capabilities of the current range of observatories. So, as you mentioned, neutron stars. So once they were beginning to regularly detect colliding black holes, one of the hopes is that you would detect colliding neutron stars. And that has since been done with the famous kilonova event. Probably 2 more other colliding neutron star events have been captured. But then you're looking for things like, say, a white dwarf colliding with a black hole, or a white dwarf colliding with a neutron star, or a star colliding with a black hole, or a star colliding with a neutron star. That would be very interesting. It would tell you about how stars are destroyed as they are interacting with black holes. But there's a limit to the size of the black holes that can be detected through the LIGO observatory. But the really interesting ones are the more massive ones, the intermediate mass black holes and the supermassive black holes. And because the supermassive black holes are so massive, so big, their mergers happen very slowly compared to the stellar mass black holes. And so the wavelength is beyond the capability of, or the frequency of those mergers is beyond the capability of the current crop of gravitational wave observatories. But the European Space Agency is working on their next generation space antenna, LISA, which is going to detect the mergers of supermassive black holes. And that's really important because, one of the big outstanding mysteries that we have in astronomy is, we know that there are these supermassive black holes at the hearts of pretty much all galaxies, and that they were present early on in the history of the universe. And in some cases, the supermassive black holes seem more massive than they should be. If you imagine you start with a star, you get a black hole finds another black hole, they merge together, they find other black holes, and you keep increasing, and the black hole's feeding on material. There's a limit to how massive a supermassive black hole you can end up with. And yet there are black holes that seem to have more mass than that. So there must be some other mechanism that is causing a black hole to be able to come together. Maybe. Or maybe they just don't understand, or maybe it was just, maybe there were primordial supermassive black holes. We just don't know. But the real magic of gravitational waves, and the one that will be the gift that keeps on giving, is that gravitational waves are a completely different way of observing the universe from the electromagnetic spectrum. And so every kind of astronomy that we have done up until 2015, pretty much, was with the electromagnetic spectrum. You look at X-rays, you look at gamma rays, you look at radio waves, you look at microwaves, you look at visible light, infrared, ultraviolet. It's all the same thing. It's all just electromagnetic radiation. You're just seeing it at different wavelengths. And so the limitations of the electromagnetic spectrum, for example, not being able to see beyond the cosmic microwave background radiation, these are all the same thing. You're just seeing different aspects of the same kind of light. But gravitational waves are an independent system for being able to measure. And one of the most interesting things that you can do with gravitational waves, for example, is independently measure the expansion rate of the universe. That when you detect 2 black holes that are spiraling around each other and merging, the chirp, the gravitational wave chirp that you get, allows you to essentially figure out the distance to this gravitational wave event. Now, right now, the accuracy is not as good as the other methods of measuring distance in the universe, but once it is very accurate, you'll know it is right in a way that you're still unsure with the electromagnetic spectrum. So that's one very exciting thing. The other exciting idea is that you'll be able to use gravitational waves to see beyond the cosmic microwave background radiation. So, we know that 380,000 years after the Big Bang was when light could finally escape out into the cosmos. And so you just literally can't see earlier than that because the entire universe was opaque. It was like the surface of a star. But the gravitational waves were passing through this material during this time. And so if we could make an even better gravitational wave observatory, it would allow us to see right to the Big Bang, that we'd be able to see seconds after the Big Bang, less than a second. We would detect the ripples, the oscillations of the universe as whatever incredible events were happening during the Big Bang. And this is, when it comes to electromagnetic radiation, this is a thing that is beyond us. It gives us additional ways to probe the vicinity around black holes as they're merging. You can detect supernovae that are asymmetrical. So if a supernova goes off and maybe blasts off one side of the supernova, like think about Mount St. Helens as it sort of detonated out the side of the mountain. If that happens with a supernova, then that would generate a gravitational wave, and that's something that you could detect. So I would say, like, of all of the applications of gravitational waves, the one that I'm most excited about is this idea of the primordial gravitational waves, the ones that get us earlier than the cosmic microwave background radiation, the ones that maybe allow us to see the Big Bang happening. That would be very cool. So there's tons more science that can be done with gravitational waves. One Air RN. Fraser, the Artemis moon lander plans seem unusually complex. Why not launch the lander, then a propulsion module, dock in low Earth orbit, rinse and repeat, not in space refueling? Yes. The plans for the Artemis mission are unusually complicated. So if you go back, let's think about how it worked during the Apollo missions. So you had the Saturn V rocket. It had 3 propulsive stages, and then you had the service module, the command module, and the lunar lander. And then it would launch into low Earth orbit. It would then reconfigure itself, and then it would fly to the moon. And then the astronauts would get into the lunar lander. They would detach from the command module. They'd go down to the surface of the moon. They would do moon stuff. And then they would get back into the ascent module on the lunar lander. It would take them back up into low lunar orbit. They would dock with the command module, get into the command module. Then they would return to Earth, ditching the lunar lander, ditching the service module, and re-enter the atmosphere in the capsule, and then deploy parachutes, and there you go. The plan for the Artemis mission is that you're going to have the Space Launch System, which is going to have the Apollo capsule on top. It's going to launch to the moon and deploy the Orion capsule into orbit around the moon. Then simultaneously, you're going to have the landing system. There's 2 possible landers right now. One is going to be the lander for SpaceX, which is the human landing system. It's going to be a variant on the Starship. It's going to go into low Earth orbit. It's going to refuel about 15 to 20 times. Then once it's got a full tank of fuel, then it's going to fly to the moon, dock with the Orion capsule, and be able to bring the astronauts down to the surface of the moon, back up into orbit. They're going to get back into the Orion capsule, and they're going to return to Earth. Sort of in the way that we just saw the Orion capsule return to Earth. That's the one idea. The other idea is the Blue Origin is building their version of the lunar lander. They're probably going to have a bigger version of their lunar lander that will also require refueling, but it's also possible that they're going to make a much smaller version that will probably just be launched on a New Glenn to the moon, and then they'll get out of the Orion capsule, get into the New Glenn, go down to the surface, come back up, or get out of the Orion capsule, get into the Blue Origin lander, go down to the moon, come back up, get back into the Orion capsule, and return. So that is a simpler system, but of course, that doesn't work. That is a simpler system, and yet that lander hasn't been tested at the moon yet. So we're still waiting for that. Nor has Starship been tested at the moon. The Chinese plan is that they're going to launch 2 Long March rockets to the moon. One is going to have the command module, service module with the astronauts on board. The other is going to contain the lander. They're going to get into the lander, go down the moon, come back up, dock with the capsule, get back into the capsule, return to Earth. So 2 launches, which is very similar to the idea of using the Blue Origin launcher. But the original idea was pretty cool. And so what you're seeing now with the Artemis is sort of after all of the compromises have been made. And so the original idea was that you were going to build the Lunar Gateway. That was going to be the next big project. Is you're going to have this space station that was going to be at this gravitational halfway point between the Earth and the Moon. And then the astronauts would fly on the Space Launch System in the Orion capsule, and they would dock at the Lunar Gateway. And then the Starship, or whatever was going to be the landing system, would be ferrying astronauts to and from the surface of the Moon. It would land on the Moon, fly up to the Lunar Gateway, dock, they get into the spacecraft, down to the surface of the Moon, come back up to the Lunar Gateway, and then transfer to the Orion capsule. And you can imagine over time that there would be multiple crews. There would be this ferry system, and you'd have people going there would be refueling the human landing system at the Deep Space Gateway, and that would feel like a much more sustainable process. And I think that is the big difference. When we saw the Apollo mission, the goal was just land on the Moon, demonstrate that we can put human beings safely on the Moon and return them back to Earth. That's it. And of course, once that goal had been accomplished, once the Soviets had been shown that they were going to lose the moon race, then the incentive was over, because there was no reason to go to the moon beyond just demonstrating you can, some minor science, but really it's a show of technological capability. And once that had been demonstrated, there was no need to do that again. And so unfortunately, the path that we're on right now, without building this other infrastructure, is going to be just, again, technological capability. Look at that. We can still put people on the surface of the Moon. That we're going to be there to stay when there is infrastructure, when there is some kind of base, some kind of station where people go to, and then they go from there down to the surface of the Moon. So, right now, things are kind of in limbo. Like, it's been really hard. It's been, throw me a pity party. It's been tough for the last couple of years for me to try and report in a cohesive way the plan for the Americans for landing humans on the Moon. It has just been, missions getting canceled. Deep Space Gateway is happening. Now it's getting canceled. We've got the human landing system from SpaceX. Maybe we're going to have the one from Blue Origin. There was Artemis 3 was going to be the one landing people on the Moon. Now it's going to be Artemis 4. And the problem comes from not having this long-term political commitment to the plan and the adequate funding to be able to carry out the plan. You've got both wandering. And so that's why we're sort of in this mess that we're in today. Yeah. Billions and billions of stars. Any chance that we could see the Pan-STARRS comet with the naked eye? Yeah. So there is a comet that is in the morning sky right now. We reported on it on Universe Today this week. I forget, A3? There was another comet that didn't survive its close approach with the sun. But there is this comet, Pan-STARRS. They're always Pan-STARRS. I forget let me see which one it is. Search on Universe Today. R3 Pan-STARRS. So we reported on that. Yeah, okay. So it's supposed to it's Comet R3 Pan-STARRS. And it's supposed to go to magnitude 0, which is definitely visible with the unaided eye, and maybe even get into the negatives. So, anything above magnitude 5, you can see with the unaided eye. And even if it's below magnitude 5, maybe down to magnitude 8 or so, you can see it with a pair of binoculars. So this one should be good. And I don't know if anybody has actually seen it so far. It peaks. When does it peak? It passes. Let's see. It passed 4 degrees on April 25th from the sun. Let me get the good time to see it. Yeah, so it reached perihelion just this weekend, and then is on its way back out, but you should be able to see it in the morning sky. Klimsky, can you show your meteorites if you have some? Sure. Let's see. I got these and this one. Oh, I need to treat it. So this is my main meteorite. I gotta hide my eyes. So this is it's about a pound, and it's a nickel iron meteorite, and it is amazing. This is a gift from my wife a couple of years ago, and it's a little oxidized, getting a little flaky, so I need to treat it with oil to sort of make it less flaky. So that's the one. And then I have a mini museum that has a little meteorite. But then this is the one that I picked up on eBay. eBay. So I have a whole bunch of small meteorites from the Campos del Cielo meteorite fall. And so this was huge metal meteorite that struck in South America, in Argentina, about 5,000 years ago, and just exploded. And there's chunks of metal all over the area. And so people go out with metal detectors and find all these little bits and pieces, and then you can just go and buy them. And so if you like open up a new browser window right now, go to eBay, search for Campos meteorite, Campos. It's Campos del Cielo. That is the sort of the cheap one that you can buy in bulk, and then you can get different sizes. You can buy ones that are like a couple of kilograms, and they're not that expensive. Like I think my meteorite was about $200, and when I buy these, they're about $20 a piece. I usually give these as gifts when I am meeting some astronomer or something. I'll bring them a meteorite as a gift. And this is a thing that I stole, an idea that I stole from Phil Plait. So he gave me a meteorite when we first met, and I'm like, I am totally stealing that idea. So yeah, it's very cool. But yeah, go ahead. Did you look on eBay for Campos del Cielo? Let me see. So a 2 centimeter chunk is about $22. A bigger one. How big are they? Yeah, you can see just a million of them on eBay. And you can buy them in bulk. You can buy them in small pieces. Yeah, they're surprisingly cheap. $20 to $100 to get a meteorite. If you want, if you're not 100% certain that what you're getting is a real genuine meteorite, definitely check into the seller and make sure it's authenticated. I recommend Aerolite meteorites. So there's a website, AERO meteorites. Yeah, Aerolite. AERO. Are they still operational? Yeah. Okay. So that is run by, or was run by, one of the people behind the Meteorite Men. And so they're legit. So the Meteorite Men was Jeff Notkin and Steve Arnold, and that was back in the 2010s ish. And so his company he was involved with Aerolite, so it's legit. So if you want to be, and see what you can buy for an aerolite. So iron meteorites for sale at Aerolite. Did I make Campos? They've got different varieties from all the different meteorite falls that have been found around the world. So a 500 gram, it's about a dollar a gram from them. So you can get a 1.9 kilogram meteorite for $960. So a 5-pound chunk of space metal for about $1,000. It's pretty cool. Yeah. So if you, if you're looking for a meteorite and you feel like you can trust the ones on eBay, then buy them there. You're looking for the Campbell's Cielo, by all means, get the certificate of authenticity. And if you want a supplier that you can trust, check out Aerolite. No, they're not a sponsor. Just, I trust the people behind that company. It is the best gift. Like, there you go. I just saved all of you who are trying to figure out a gift to buy a space nerd. Buy them a meteorite. Let's see. Frosty Winnipeg, why is it flaking? So the meteorite is flaking because it's oxidizing. It's rusting in the atmosphere. And so it's just, I have to keep it oiled for it to not, like, I essentially spray a little bit of WD-40 and oil the exterior of it to protect it. Put a layer on top of it. Shadow Mask, what's your NHL playoff pick? I don't follow hockey, so you're gonna have to ask a different Canadian. I know it's sacrilege. Identity just tuned in, but assuming you've covered the failed target orbit Blue Origin launch. I haven't covered it. I haven't really investigated it yet. We'll be covering it on Space Bites on Thursday. And so I'll sort of, in preparation before Space Bites, I'll sort of jam all the information about the launch into my brain. We're going to be reporting on it on Universe Today this week, though, probably tomorrow. So there'll be a story about that. It sucks. It's so sad. Tack Mace, first time in the YouTube live stream. I missed the context on why you hide your eyes when you hold the meteorite. Well, the problem is that my, if I want to show you something, like here's a weird little plug for my watch. Check it out. Do you see the problem? So if I hide my eyes, then the face tracking no longer goes after my eyes and goes and looks at something else. So as long as I have my eyes visible, then the face tracking on my camera will always lock in on my eyes and won't let me show anything else. So that is the right behavior. That's good. I like that. I want to show you, a Kindle. It's going to be out of focus. It's always going to be out of focus until it's at the same distance as my face. And like getting a camera that has really good autofocus, so I can be close up and it's focused, and I can be far away and it's focused, is the best. And Sony is really the only camera manufacturer that gets autofocus right. All of the other cameras have this awful searching focus. So it'll if you get out of focus, it'll like go a little farther and then it'll go back in, and it's like searching for focus. And the Sony one is just rock solid. I can trust it. So I've switched to autofocus. I've switched to Sony cameras about 5 years ago. I got the A7C And now I've got the FX3 as my camera, my streaming camera, purely because the autofocus, and it doesn't overheat. So before I had the Sony A7C, which was a good camera, but it would overheat. And so I'd be in the middle of a live stream. The camera would be running for an hour and a bit, and then it would just go turn off. And so that was suboptimal. And so now it's, this camera is designed for video. And so it works really well. I don't use it for, like, it's a very good camera, the FX3 camera, but I don't use it for what it should be used for. Like, it is, you can use these for Netflix. So if you produce a video, if you want to make a series for Netflix, this camera is on the approved list of cameras you can use for Netflix. But I don't, I dramatically underuse it. It does exactly what I need, which is it doesn't overheat. It does 4K, 60 frames a second, and it has a really good autofocus. That's all I care about for this camera, because everything else just kind of underperforms in those respects. Misaleki, are the NASA Venus probes happening? I don't know. So the White House administration released its skinny budget about 2 weeks ago, and this was their request for the upcoming NASA budget. They're requesting about a 25% cut to NASA's budget, and they're looking to put a 55% cut to NASA's science budget. They're looking to cancel about 50 missions, and that would definitely include the Venus probes, so the Da Vinci Plus and the Veritas missions. But they did this last year and tried to suggest the budget that they were looking for, and Congress overruled the budget, and so it didn't go through, and all of the funding was restored to all of the missions. Although thousands and thousands of engineers at NASA were kind of pushed out, took early retirement, contractors were removed from various agencies at NASA. So it was a bad year for NASA last year. This year, who knows what's going to happen, whether that skinny budget will actually go through. I doubt it at this point. I mean, we saw what happened last year. Congress pushed back, grew a spine, pushed back against the cuts to NASA, and all of the missions that we were so nervous about remain. Now, people need to be vigilant. So, I'm sure all of the people who are advocating for continued NASA exploration will continue to do that. But the Veritas and the Da Vinci Plus missions were on the chopping block. So if the skinny budget goes through, if NASA's budget is cut back, then those missions will be canceled. If NASA's budget is not cut, then those missions will limp forward another year. But what are the chances that they're actually going to make it all the way through this process, changing of administrations and on and on and on? Who knows? Things are very fluid right now at NASA. Things are changing in the U.S. government right now. So who knows what the implications of all of the stuff that's going on right now will be on the future of space exploration. The goldfish fish. Why does Saturn's moon Iapetus have that huge equatorial ridge? And why don't we fully know how it formed yet, even after Cassini? So we think we know how Iapetus got its ridge. It probably ate a ring. So if you look at the position of the ridge on Iapetus, it's sort of along its equator, and And Iapetus is has one side of it that is dark and one side of it that is light. I actually did a whole video about Iapetus on the channel, why I love Iapetus so much. It is seriously one of the most interesting moons in the solar system. One of the moons of Saturn, really bizarre. And if you look at it, it's like one side of it looks speckled in tar, and then the other side is bright. And what seems to have happened is that the moon was tidally locked to Saturn, was going around Saturn, and it passed through or gobbled up a ring. And so one side of it is the sort of this previous darker material on the surface of the moon, and then the white side of it is the part where all of this sort of snow and ice impacted into it. And then where that ring came in, it built up this material into this ridge on Iapetus. So it's still a bit of a mystery. We got a lot of information from Cassini. It is a very cool moon, one of the coolest in the solar system. Luke Skywalker, what do you think about the fusion ion engine produced by Pulsar Space? I haven't reported on this. So they've got a Hall effect satellite thruster. And they're working on a direct fusion drive. So I've reported on some direct fusion drives in the past. I forget the name of the company. I'm sorry. I've got it was an interview with one of the NIAC winners 2 years ago. And one of them was it Safe Nuclear Reactors? Oh, direct fusion. Let's see if the company. It was a name like that. Fusion powered orbital lander. That's the one. $2016. No, that's not it. Okay. Well, this is becoming boring. Yeah. So the gist is like the traditional idea of a fusion reactor. We think about, say, a tokamak reactor, where you've got this magnetic containment area where you've got the hydrogen that's flowing around inside of it, and you are containing it, and you're creating the conditions like the inside of a star, and then you are generating more power, more energy out of it than is going into sustaining the reaction. And that, there are these giant fusion reactors that are being built on Earth, like ITER, and there's the Chinese are doing one, and there's some in Germany. And these are very large structures, but you can make a kind of fusion drive that is more like a bomb, where you are essentially fusing pellets of hydrogen. You're doing this and you're generating energy, and then you're using that to heat up some kind of exhaust gas, and you are firing that out the back of your engine. And this is a theoretically possible. People have been working on these ideas for a while. Seems like it's more likely to be the kind of rocket that we would have in the near term. And like, they have been awarded NASA NIAC grants. Like, this is serious technology. And so I'm not specifically, I don't know about their ion engine. So I would have to watch, read the paper, read their announcement. But like, in general, you should be just mildly skeptical of any of this kind of stuff, that these technologies, even if they're tested in the lab, it's going to take a while before they can actually be useful in actual space flight. So they need to demonstrate that they can do all of the things that is expected of them in the lab, and then to make that space hardware ready is a whole nother level of technological development. So all this is exciting. It'd be great to have a sort of faster method, something that can use the fuel more efficiently than a chemical rocket, because chemical rockets they're so limited. I mean, they give you a tremendous amount of acceleration in the beginning, but the fuel runs out in 8 minutes, right? And then you're done. You want something that can use the fuel more efficiently, deliver higher delta V over longer periods of time. With higher delta V, you can do things like sample return missions from interstellar objects. You can travel out to Pluto or out to the solar gravitational lens in a human lifetime. So hopefully someone will come up with a better system for being able to operate. And I wouldn't be surprised if it ends up being fusion, either some more advanced fusion that is based on these kinds of fusion reactors that we're seeing developed down here on Earth, or this kind of more rough and ready direct fusion where you are detonating hydrogen and using the energy for various purposes. Ivo Drinkovic. I can't understand how we can look in any direction in the universe to see the Big Bang. So the Big Bang happened at a certain time, happened 13.8 billion years ago. And it happened everywhere. That every part of the universe is moving away from every other part of the universe. In general, like obviously locally, you are not breaking apart. You are not being pulled off of planet Earth. The Earth is not being pulled away from the sun. The sun is not being pulled out of the Milky Way. Milky Way and Andromeda are moving towards each other, but that's it. Everything else, if there's a galaxy that is 5 million light years away from us, even though there is gravity that is attempting to pull those galaxies together, the expansion of the universe is pulling them apart faster than they are pulling themselves together, right? So that expansion of the universe is happening everywhere. And that if you then roll the clock back, you look at this object that is at the far right-hand side of what you can see in the universe. Then you look at the object that it's at the far left-hand side of the universe. 13.8 billion years ago, those two places were the same. They were right beside each other. Now they are 93 billion light years apart, but 13.8 billion years ago, they were at the same location. And so when we look out into space, we are looking back in time. And the farthest that we can see is the cosmic microwave background radiation, which is about 380,000 years after the Big Bang. And it is when the light could first escape out into the universe. And every second that goes by, you are seeing one light second farther into the past, farther away into the universe. The next light is making its way to you. And so everywhere we look, we are seeing back in time, and that the Big Bang happened everywhere. And it is still happening everywhere. Wherever we look, we see the Big Bang. The galaxies are getting farther and farther away from each other. Alchemist 2000. Is there a Lagrange point between the Milky Way and the Andromeda galaxy? So to get a Lagrange point, you need to have a very massive object like a star, and then a lighter object like a planet, or a planet and a moon. Andromeda and the Milky Way are roughly similar. I can think the Lagrange points don't really kind of kick in until about 50, at least 50 times mass difference. And then the other thing is that the Milky Way and Andromeda the Milky Way isn't orbiting around Andromeda. The Andromeda and the Milky Way are kind of on a collision course with each other. And so you wouldn't really get a Lagrange point until you got some kind of stable orbit where you would actually get these Lagrange points. And then the other thing is that, the star is effectively a gravitational point. The Earth is a gravitational point. Now, obviously it's not, it's a blob, but still. A galaxy is this giant, diffuse halos surrounded by this dark matter. It's a blob. And so it's very hard to have this very specific spot where you're going to get this this Lagrange point. But if you had a galaxy, a dwarf galaxy, was orbiting around the Milky Way and it was far enough away and it was orbiting in this stable way, then you would probably get Lagrange points between the Milky Way and some dwarf galaxy that's orbiting around it, some satellite galaxy. The same forces always show up, just at different scales. João de Carvalho. Roughly how many departments dedicated to UAP studies exist in universities? I don't think there's any. But, you know, like what are the fields that are involved with UAP studies? Weather satellites, astronomy, obviously, military intelligence gathering is probably the closest. So maybe there are groups at military universities that are studying various sensor objects, stuff on radar, things that they don't recognize, to try and figure out, you know, what is absolutely an incoming drone and what is something else. They don't really know what it is yet. Louis Nelson Smith, can you explain how DESI works and how is the instrument being used to detect dark energy? And what is dark energy anyway? Yeah, I could try. So DESI is the Dark Energy Spectroscopic Instrument. It is one of the major experiments that are being done to discover or understand the nature of dark energy better. And so the big question, or the effect of dark energy, is that it seems to be accelerating the expansion of the universe. That astronomers went and looked at this very specific kind of supernova, type 1a supernova, that is known to give off a very specific amount of energy when it explodes. You know how much intrinsic brightness is in the supernova. And so when you find one of these objects and you measure its brightness, you know how bright it should be. Therefore, that tells you how far away this thing is. And so when astronomers were measuring all of the type 1a supernova that they were seeing, they found that the ones that were older were farther away than they should be, and what you would expect in the expansion of the universe. And there's this very sort of smooth curve. And it appears that there's this additional expansion that's happening in the universe above and beyond just the regular expansion, thanks to the Big Bang. And so this was coined, this is dark energy. We don't know what it is. We don't know what's causing it. We don't know how it started. It just seems to be that the universe is more than just expanding. The acceleration of the universe, the expansion of the universe is accelerating. And so that is dark energy. So once you discover this new thing, once you discover this collection of observations, then you need to make better observations because people have a ton of questions. And so there was a whole bunch of surveys that were developed to be able to help understand this. There is the DES, the Dark Energy Survey, which wrapped up its first, I think, 5 years of its survey, and it was taking images of the sky and then they're using that to kind of measure the galaxy clustering and looking at supernova and things like that. Then there's of course Vera Rubin, which has just come online, and it's going to be able to detect tons and tons of supernova, over 1 million of these type 1a supernova. So it will give astronomers much better data on finding these. It's going to find other events related to that. You've got the Euclid mission, which was launched by the European Space Agency, and this is essentially taking infrared images of the sky to determine the composition of galaxies, as well as visible images to see how light is being distorted around galaxies, and that allows you to kind of measure where the dark matter is and be able to understand the history of the universe at different time slices. There's the upcoming Nancy Grace Roman telescope, but the one you're talking about is DESI, which is the Dark Energy Spectroscopic Instrument. And this is a ground-based telescope, and it is doing a survey of the night sky, and it just wrapped up. It completed 13,000 degrees of the night sky. The whole sky is about 41,000 degrees, so it's like a little under a third of the entire sky. And so what happens is, and this is sort of a technique that's been done for a long time, which is that you want to measure the chemical composition of a galaxy. And so what you do is that you have what they used to do is they would use a plate, like a aluminum plate that they would put in front of the telescope, and it would block all the light from the telescope except for the galaxy. And so they would take the telescope, they'd point it at the region that they were going to look at. They would put this plate in front of the galaxy, they put this plate in front of the telescope, align it perfectly, or put it in front of the instrument, that the camera that measures it. And then only the light from the individual galaxies would be allowed through these little pinprick holes in the plate. And then they could expand the light from each one of those galaxies to do spectroscopy on that light and determine what that galaxy was made out of. And then you could tell which are the galaxies that are relatively close to us, which are the ones that are very far away, which are the ones that have been heavily redshifted and are seen earlier on into the history of the universe. But it's a laborious process. You can imagine, you can take a new picture, you got to pull out the right plate, put it in front, drill new holes in, right? So with the DESI survey, they have this field of little fiber optic cables that are on these little actuators. And so then they line up, they know all the galaxies they're going to see in the field of view. They line up all the little fiber optic cables to line up perfectly with the positions of the galaxies, and then they take their picture. And so the light from that one galaxy goes down the fiber optics down this one channel, and they're able to separate the light and be able to analyze it separately from all the other stuff that's out there. And that gives you really good, clean data on that. And so what DESI is doing is that they are looking at the history of the universe. They're looking at what was the expansion rate of the universe at different times in its history. And they just wrapped up their 5-year mission to explore new galaxies. They wrapped up their 5-year observing campaign, and so and are in the process of releasing all the data. And so the scientists are going to be able to use this to calculate. And what you're going to get is just, you'll be able to see, these are the galaxies that we're seeing relatively nearby. These are the galaxies that we're seeing 1 billion light years away. These are the galaxies we're seeing 5 billion, the quasars that we're seeing 5 billion light years away. And then you can measure the expansion rate of the universe at different times in the history of the universe. And that'll allow you to see, is dark energy changing over time? Because this is one of the big questions that we have. We know that the expansion of the universe is accelerating, but is it a constant acceleration? Or is the actual strength of the dark energy changing? And the initial results from the dark energy survey, the DES, said actually it looks like dark energy is dynamic. It's not this constant, that it appears to be decreasing over time, which is good news, because if it's increasing over time, then that could lead potentially to the big rip, right, where the universe tears itself apart. So it appears that it's the opposite of that, that there is a slight decrease in the amount of dark energy that is entering the universe for every cubic meter of space. But there are 4 different methodologies for measuring dark energy. So you have the Type 1a supernova, you have the galaxy clustering, you have the gravitational lensing, and you have the baryon acoustic oscillations. And the problem is that 2 of the measurements done by the Dark Energy Survey indicate that it is more consistent that the universe is, the amount of dark energy is decreasing. But then 2 of the measurements methods give the opposite. And so that is confusing. That is not what you would expect. And so now we're going to get these additional surveys, the DESI survey, Nancy Grace Roman, Euclid, Vera Rubin, and on and on and on. And so at this time when we have all these questions, where this mystery is unfolding, we also happen to have the perfect tools for the job. That 5 different brand new top of the line spacecraft have been launched with the capability to give us an answer on this question. And so we will look back on this time, say 10 years from now, in the way that we look back at pre-Gaia data. Before Gaia, we're like, where are all the stars? Which stars are moving? I don't know. Gaia told us where 1.8 billion stars are, where they're moving, what they're made out of. It's incredible. And that's the same kind of revolution in historical, astronomical, cosmological data that we're about to get, thanks to all of these missions. So DESI is the second one out now. You have the DES, now you have DESI, and we're just going to see more of this information come out over the coming years. I'm Starshine. How far away do you think they are from understanding dark matter and dark energy? I mean, we have no idea what dark matter and dark energy are. The best that we can do is improve the observations right now. Like, obviously it'd be great if someone suddenly detects the particle for dark matter in the lab, boom, done, explained. But more likely, we're just going to get better and better observations that up until this point, we had this series of observations that told us that there was something going on, right? You measure the rotation curve of a galaxy and it tells you there's something going on. You look at the gravitational lensing of the light that is coming from galaxies and you can see this giant halo, this gravity blob that is around a galaxy, and it tells you there's something going on. That the dark matter is this collection of observations in the same way that dark energy is this collection of observations. And what is the underlying cause is unknown. And we may never know the answer, although I think that's unlikely, but we may never know. But we will at least be able to constrain it, that we will, I talked about earlier on this episode, I talked about all these different missions that are coming online that will map the universe in this cosmological sense, just all of the characteristics of the universe at different times into history. And that will allow you to tell, is dark matter or dark energy, are they changing over time? How do they clump? How do they interact with regular matter? What are the conditions that you find it? You can rule out lots of theories. We'll get to this point where you can potentially rule out other alternatives to dark matter, like, say, modified Newtonian dynamics. You could say, okay, no, dark matter is not that we don't understand gravity at the larger scales. It really is that there is some kind of invisible particle that is causing these effects. These are the kinds of places that we're going to get to. And when we get to this place where, like, it has to be a particle and the particle has to have a energy level that corresponds to this, and that if we could build a particle accelerator that's capable of producing particles, we could target the energy levels in the particle accelerator to try and produce them. So I think I would say, with the current crop of the telescopes that I mentioned earlier on in this episode, we will get to a place, I would say, within about 10 years. The end of, like, DS has already sent out its initial results. DESI has just wrapped up its 5-year mission. The Vera has begun its mission and will run for 10 years with its LSST. Nancy Grace Roman comes online next year, 2027, and the Euclid mission is already operating and will release its first data set in the next couple of years. That we will have, these will have delivered their conclusive answers within about 10 years from now, and that we may still not know what the explanation for what dark matter and what dark energy is, but the measurements will be precise. And I think a great example of this is the cosmic microwave background radiation. We first discovered the presence of the cosmic microwave background radiation, the afterglow of the Big Bang, back in the 1960s, or in 1964. So it had been theorized that if the universe was once in a more compressed area, then you would see this time when the entire universe was like the surface of a star, and that you would then see this radiation in all directions when the light could finally escape, this time of last scattering. And astronomers were working with this radio telescope, and they detected this background noise in their observations. They couldn't make it go away. And then they realized that they were detecting the cosmic microwave background radiation. Then there were these surveys of the cosmic microwave background radiation. And so there was, the first one was the Comet survey, which was done like in the 1980s. And it could just barely detect that there were temperature fluctuations in the cosmic microwave background radiation, confirming a lot of the theories about the Big Bang. And then you got the Wilkinson microanisotropy probe, the WMAP, in late 1990s, 2000, and it had even better resolution of the hot and cold blobs in the cosmic microwave background radiation, giving a better measurement of the age of the universe, giving more confirmation, better, helping to sort of tune in our understanding of the universe. But most recently, we got the Planck mission, which did the highest resolution, literally reaching the limits of what can be observed in the cosmic microwave background radiation, that you pretty much can't resolve it with any higher level of resolution. And that is the process that you go through. And so now we're at this place with the Planck data. The next step is to try and pull out polarization data out of the Planck information to maybe try to detect, say, primordial gravitational waves. But you're at this point where you finally have sufficient data to be able to understand, to be able to totally rule out certain ideas. And I think maybe 10 years down the road from now, so say mid 2030s, we will have all of those surveys will have delivered some version of their science data. And we will have a much better understanding of the constraints of both dark matter and dark energy, what influence they played on the universe at different eras, where it's clustered, where it's not. Is dark energy increasing or decreasing over time? Is it perfectly, is it homogeneous across the entire universe, or is it concentrated in certain areas? Like, these are all the kinds of questions that we will get answers because the measurements are so difficult to make. So that's where we stand right now. So stay tuned. 10 years, I would say. But I don't think I would be surprised if somebody uncovered the cause of dark matter, like actually detected the particle within 10 years, or if somebody detected the cause of dark energy, that if they were able to just generate dark energy in the lab. I would be surprised if in 10 years that happened for either one of those. So we will have a really good measurement, really good observations for both of them, but I suspect we still won't know what they are, which is fine. This is the mystery. It has to unfold. It takes as long as it takes. Neil Greening. Surely, if the true universe was once small and finite, it can have grown, but it can never be infinite. So this is a misnomer that I really try to deal with whenever it comes up, which is, the traditional science explainer is that the universe was once this tiny singularity, and then there was the Big Bang, and now we have the infinite universe around us today. And that is not an accurate explanation of what it was. That the observable universe, now we have this radius of universe around us that is, is 93 billion light years across today. And so 13.8 billion years ago, that entire 93 billion light year across universe was, say, the size of a grapefruit. But there was more universe outside of that. that there was another grapefruit right beside it and another grapefruit beside that, that, at that moment, our observable universe was the size of a grapefruit, and now it has expanded to the size that it is today. But the universe was probably, if the universe is infinite today, the universe was infinite at the time when the observable universe was that grapefruit. That you always have to sort of switch between the observable universe and the actual universe, the real universe, the full universe. And we don't know how big the full universe is. It is at least thousands of times bigger than the observable universe, because if it was smaller than that, if it was finite and smaller than that, we would measure the curvature of the universe, and that would allow us to know how big the universe is. The analogy that you always use is planet Earth, right? You stand on the surface of planet Earth and you can't tell how big the Earth is just with your eyes alone. It's only when you perform experiments, checking the lengths of shadows at different locations on Earth, do you actually start to calculate the true size of planet Earth. And it's the same thing, that when we're in our observable universe and we measure the larger curvature of the universe, it appears flat. It appears infinite. But it could just be that it is so big. You can imagine if the Earth was so big, if the Earth was millions of times bigger, that you wouldn't be able to measure the size of the Earth. It would always appear to be flat, no matter where you go. But it would be a sphere. It just would be so big that you wouldn't be able to measure it. But it is not that. And so we can calculate, we can measure the true size of the Earth. And so the universe is either too big to measure or infinite. And at the beginning, 13.8 billion years ago, it was too big to measure or infinite. It was infinite then, and it's infinite today. Deant6361. Will New Horizons end up leaving the solar system similar to the Voyagers? Yeah. Now, New Horizons is on an escape trajectory out of the solar system, and so it is going to leave the solar system in the same way the Voyagers. We have sent 5 spacecraft so far on escape velocities from the solar system. So the Pioneers, Pioneer 1 and 2. Wait, was it Pioneer 10 and 11? Yeah, Pioneer 10 and 11. The Voyagers, Voyager 1 and 2, and New Horizons. Those are the only spacecraft that have been sent on an escape trajectory out of the solar system. And so they are going to head out of the solar system and begin orbiting the Milky Way as if they were stars. Mr. Al J. Mitchell. Is space expanding like raisin bread? Mr. Al J. Mitchell. Is space expanding like raisin bread or stretching like a rubber band? The raisin bread analogy is the good one. Absolutely. I wouldn't use the stretching analogy because it would mean that there's some kind of tension that is looking to kind of pull the universe back together, although there kind of is, which is the gravities. But we'll talk about the raisin bread analogy first. So, people always use this example of raisin bread to kind of wrap your mind around how when we look in all directions, we see galaxies moving away from us. In the same way that if we were baking raisin bread, that the rising process would move the raisins away from each other. No matter which raisin you're on inside the raisin bread, if you looked out at all the other raisins, if the bread was transparent, then you would, as the bread was rising, you would see the raisins moving away from you. No matter which raisin you were standing on, all of the other raisins would be moving away from you. And that is the analogy, except scale that up to the entire universe. Instead of raisins, you've got stars, and instead of bread, you've got just the vacuum of space, right? But that process is the same. But this idea of like stretching like a rubber band, it kind of does come into play in that the future of the universe depends on the mutual gravity of all of the stuff that is in the universe. And so one of the questions that astronomers had early on was, what does the future hold for the universe? One possibility is that the mutual gravity of the universe is so strong that even though it has undergone this big bang, it's had this initial momentum that has caused everything to move away from each other. Everything is slowing down. And eventually the mutual gravity of everything is going to pull everything back together, and then it's all going to come back together into a big crunch. And then maybe you get another big bang. You get a bounce after that big crunch. And then the other possibility is that the universe is just going to continue expanding forever and like coast to a stop right at infinite time. And then the other possibility is that the universe is going to expand forever, and even at infinity, it will still be expanding, but slowing down. And those are kind of the three assumptions that astronomers made when they were doing their surveys about the expansion rate of the universe. And of course, in 1998, when they were looking at the historical expansion of the universe, looking at the Type 1a supernova data, the thing they found was, no, wait, it's not going to come back together. It's not going to come to a halt at infinite time. It's not going to continue on expanding forever. It is accelerating, that the speed of the universe is increasing. The expansion rate is increasing. It was this fourth mystery option that nobody was anticipating. And yet it appears to be the dominant force in the universe. Dougal, how far ahead has China planned for their space endeavors, space stations, multiplanetary missions? How much of those plans are publicized? So China has a sort of series of layered plans. So they have, I think, like a 30-year plan, and then they do 5-year specific plans that they release. And so the 5-year plan for China includes the Chang'e 7, Chang'e 8 missions, the Tianwen missions, the work that's being done with the Chinese space station, and then the upcoming upgrades to the Long March rocket, the Lanyue lander. I forget the name of the capsule. Anyway, so the new hardware to support both replenishing astronauts on the space station as well as sending humans to the moon. So that is, and they've got a bunch of other space telescopes and other things that are in the works. And they've got these 5-year plans, and they're public. You can go search for the Chinese. Let me see what it's called. The Chinese 5-year space exploration plan. I forget what they call it, but they send these out every 5 years. And then they have this longer plan as well with larger, rougher timelines and they tend to follow them. So the rougher timelines, the larger kind of sort of priorities about human space exploration, scientific discovery, space technology, space military, etc. They find their way into the 5-year plans. They're sort of pulled out of the larger plans and moved into the 5-year plans. But they have these 5-year plans across all of China. So, yeah. But I would do a search for 5-year plan China, and you should be able to get it. We reported on when it was announced. I think it was like February. What was the last one? So their 15th. Oh, they just released their 15th 5-year plan. Okay. April 17th. Yeah. Okay. Maybe we have a story in the works on this on Universe Today. Okay. William Hallman, what is your opinion on scientists and physicists being killed randomly and tied to the anti-gravity propulsion science? I haven't heard about this happening. So there's a follow-on by to Carvalho. So are the strange phenomena in the skies that no one is studying? You were talking about how many people are at universities. So there are some strange phenomena in the skies. There are unidentified aerial objects, and there are people not studying them. So, so far, when you have people like Mick West and stuff who go through the video that have been captured of things, then they get identified, and they're often very bland answers to what they are. But there are tons and tons of things. Like there are plenty, like it all depends on the field. So for example, in astronomy, there are unidentified objects that happen all the time in various telescopes, in radio telescopes. Think about fast radio bursts, little red dots, blue transient objects. There are just stuff that's happening in the solar system. There are all kinds of previously unidentified objects that are seen in telescopes that are then people go, what is that? And then they begin studying them. And so you could say that there is, like, every astronomer is looking for things that have previously been unidentified that are trying to make some sense of what they are. That is the purpose of science, is that you are looking for things that are happening in the universe in terms of nature that are not understood, and then you're attempting to understand them better. And it's up to the individual astronomer on what it is that they want to focus their energy on. Right. I know you are excited about the work done by Beatrice. What's her last name? I forget how to pronounce her last name. We've reported on her on Universe Today. Vera Oil. Yeah. So, she's seen examples of objects moving in the sky before there were satellites launched from Earth. So she is an astronomer, a trained astronomer, who is trying to explain this, trying to come up with an answer for this. So there are plenty of unidentified phenomena, and there are plenty of astronomers who are finding these things intriguing and interesting, and in some cases building instruments designed to study them. The problem is that a lot of it all depends on the quality of the data. How good is the telescope that is turning up the thing that people are trying to study? There was a recent study done by NASA where they were looking at UAPs, and they found that the problem is that there just isn't enough good quality data, that, people are mentioning stuff anecdotally, or they've got a blurry picture they took with their camera. And so if you wanted to get a better survey of the night sky, then you would have to invest money in telescopes to scan the night sky. And until people are willing to put that kind of expense in compared to other kinds of expenditures, then people will search where the data are good. Science compliance. How did you feel about the Project Hail Mary movie? Just watched it today. I loved Project Hail Mary. I love the book, and I really enjoyed the movie. It's a very simple movie. It's about, it's a movie that makes you feel good. The book makes you feel good too, right? You don't walk away feeling profound new understandings of the cosmos. You don't feel like you've been challenged emotionally and spiritually and conceptually. You walk out of that going, that was fun. I feel happy. I really enjoyed that movie. I really enjoyed that book. And Andy Weir is great at that. I'm going to sneeze. Andy Weir is great at doing, a compelling book that you are very entertained by. It's funny. I'm reading Dune right now, just kind of rereading it for the first time in about 30 years. And we just rewatched the Dune movies. But probably going to go watch the 1984 Dune, and maybe the TV series was on Sci-Fi. I'm kind of Dune obsessed right now. But I'm reading the book, and it's so good. It's so good. It is a masterpiece. It is easily the best science fiction story ever written, and it just holds up. There's little bits and pieces that are very kind of anachronistic to the sci-fi flavors of the 1960s, the kind of way that sci-fi authors talked in the 1960s, but just the detail of the writing, the characters, there are some tropes, but like just in general, if you watch the movie and you're like, I really enjoyed the Dune movies, the books are so good. And you can feel that there is this difference, that there is, in the Andy Weir, in the Project Hail Mary and in The Martian, there are these really complicated, dangerous, scary events that happen. And through creativity and science, our hero navigates the problem and comes up with an answer. And it seems like all hope is lost, and yet our hero is able to come up with a solution to the problem. And that is very satisfying, especially as a person who understands the science, understands the framework that this is done within. But the stakes on the story, the kind of story that he is trying to tell is relatively simple, right? Is like, can a human, like, what would a human having a friendship with an alien where you had to rely on each other and yet had no common ground beyond mathematics, how would that unfold? And that is the story that is being told in Project Hail Mary, and much more in the book. Like in the movie, they shortcut all of that stuff and get you to kind of the good stuff right away. In the book, they spend a long time just trying to figure out, how do you even begin to trust the other entity? And that is really well done. And sort of, it is a buddy movie, a buddy story, but one that feels like a very realistic, best possible realistic attempt at trying to explain how that would unfold. It's great. It's great. I loved it. But like, read Dune. If you want to sort of feel like a story that just takes it to the next level, Dune is just unbelievable. So good. All right. We've reached the end of the episode. So thank you, everyone, for hanging out with me today. Thank you to the moderators who were sticking around. I think Zapfan's here. Maybe has gone to bed. Oh no, there he is. Okay. What do we got coming up? We got a new interview we're releasing on Wednesday. And I mentioned this in the QA that we're going to release tomorrow, that we've been making all of the live streams public, and not just the recent ones. Like, this one's going to be public, but we're actually going back in time and we're releasing all of the previous hidden live streams, putting them all public. So you're going to see like a whole bunch of new videos coming from me, but those are us just turning the unlisted live streams public, because we have been convinced that the YouTube algorithm is not punishing us for doing this. So if you want unlimited viewing while you're gardening or working on some woodworking project or trying to go to sleep, you're going to have hundreds of 2-hour long live streams available to you. All right. Thanks, everybody. I'm going to go, what am I going to watch? I think I'm going to watch Dune 1984 now. I think I'm stoked to go and watch that old version of Dune. So thanks, everyone. And we will see you all next week.